Good afternoon, everyone. Today we have the privilege of hosting Mr. Anuj Kumar Singh, sir, a dedicated researcher at the Laboratory of Optics and Quantum Materials (LOQM) in the Department of Physics at Indian Institute of Technology, Bombay. Anuj sir is an alumnus of University of Lucknow and has been contributing significantly to the field of photonics research. Joining IITB in January 2019, he has played a vital role in transforming LOQM from a mere room to the best quantum optical uh, uh, and growth and processing laboratory. Despite the challenges posed by the COVID-19 pandemic, Anuj sir and his team seized the opportunity to plan and build an impressive array of capabilities at LOQM. Anuj sir has demonstrated exceptional leadership as the president, vice president, and treasurer of Photonics Student Chapter IITB, sponsored by Optica and IIIT Photonics Society. Please join me in welcoming Mr. Anuj Kumar Singh sir to our talk session today. Over to you, sir.
Thanks, Aman, for a kind invitation. I'm Anuj Kumar Singh, final year PhD student, senior research fellow in Laboratory of Optics of Quantum Materials. So basically, I am working on the quantum photonics using low dimensional materials, or you can say low dimensional emitters. So today's topic is reshaping the fascination of quantum world by using low dimensional emitters. So I will just show my content in some pictures. So suppose we have a emitter or dipole which is emitting like this. So we call it as an intrinsic emitter. Okay. So now if suppose we have a cavity and we can bring that emitter near to this cavity. So what happens? There are some changes in this emitter will happen, and that changes corresponds to emission enhancement in this emitter. There should be some strain can be generated in the material, and then due to the strain, the band gap changes and the wavelength shift should happen in this emitter. Third is like suppose this emitter is have a simple two-level system and emitting like a simple like this. And if we can bring it near to the cavity, the defect states in this emitter can be induced, and the band gap can be changed. The third, and if suppose we can bring this emitter inside the cavity, so that cavity is called the monolithic cavity, and then we can basically engineer the WGM modes, which is called whispering gallery modes, inside the cavity. So basically, I'm engineering the emitter's property by keeping it near to a cavity. Okay. So before it starts, always I keep thanks to these two guys, which is Andrea Game and K. Law. So basically, these two guys provides us a technique to exfoliate the two-dimensional materials to in the regime of monolayer. So there are lots of monolayers, lots of two-dimensional materials are available from basically insulator to superconductor region of material property. So I'm basically working on semiconductor and HPN material. So these two, why we call it in two-dimensional materials? Basically, two-dimensional materials because they are confined in basically two dimensions. Okay, so that's why we call it two-dimensional materials. Now, why they are active in the optics field? So when we are moving from the bulk to monolayer, regime, so we can change the band gap from indirect to the direct band gap. Okay, so that the enhancement of the photoluminescence can occur from bilayer to monolayer. You can see in this picture. Okay. So that's why these are much optically active materials, and we can use it in the optical devices as well as for the optical spectroscopy and fundamental studies. Okay. So statistics of the two-dimensional materials, you can see here lots of publications are coming in last few years with these two-dimensional materials, and you can see the lots of work with done with the MOS2 and other materials. I used to WSE2, which is tungsten diselenide. So why I used WSE2? Because it have nature of ambipolar. So since MOS2 is have nature of basically N type, and other is like black phosphorus P type, but WSE2 have ambipolar nature, so we can use it for basically both. So in these two-dimensional materials, so basically the I can say path emission can be responsible for the excitons. So what are the excitons? Okay, so suppose we have a basically this is a comic way of understanding these excitons. So suppose we have our simplified atom where negatively charged electron and positive charged nucleus is there. Suppose we can incident a photon on this. So what happens? This electron goes to the higher state, higher energy state, and leaves the hole. And if this electron and hole will combine with a Coulomb interaction, and it is bounded by, then this electron hole pair is called basically exciton. Okay, so that is basically exciton, and have lots of photovoltaics, flexible solar cells, and other applications in this. So these excitons lies in three-dimensional materials also. But why these are important in two-dimensional materials? Because in two-dimensional materials, they are showing less screening, if less dielectric screening effect, so that their lifetime is high, and that can be useful for novel photonics applications. So here is the band gap of the TMDC is shown. So in this band gap, mainly the bright exciton is responsible for the emission, while there are lots of dark exciton is there. If I am saying dark exciton, it means the exciton which is not optically active. So we need to optically activate for somehow. So basically there are spin forbidden and momentum forbidden dark excitons. That means spin selection rules cannot follow in the spin basically forbidden dark excitons, and in momentum there is we need extra momentum to activate these basically excitons. So that is called basically exciton. These excitons are mainly needed for application of two-dimensional materials. Okay, for emission application of two-dimensional. So first, I asked the question, can we enhance the emission of these two-dimensional materials by using nanophotonics tools? So I will be little fast from now. Basics, so here I basically fabricated a cavity as a nano cone, and then we integrated a WSE2, and then we used the basically this uh, plasmonic enhancement of these two-dimensional materials for application of basically enhancement of two-dimensional materials. So we fabricated this simple low-cost method by using polystyrene beads. So here we have polystyrene deposition, and then we had self-assembly of these polystyrene beads, and then we etch it out by using oxygen plasma. And after that, you can see we have the nanocone formation. Here is the this part of real image of SEM image is shown here, and the nanocones are shown here. So these are PTFE nanocones. PTFE is nothing but simple Teflon, and then we can deposit a 100 nanometer thin gold layer on top of that. So we have two samples. One is the gold nanocone, and another is the PTFE nanocones. Then further, we growth by standard CVD growth method, the monolayers. The monolayers of WSE2. Here you can see WSE2 monolayers are how we can how we got to know these are monolayers. You can see the thickness is the 0.8 nanometer, which is basically 8 angstrom, basically a single atom thickness of WSE2. And from the Raman spectroscopy, we also confirm that these are the monolayer samples. So once we have these monolayer samples, we integrated it by using wet transfer method. But there is a challenge of integrating because of the hydrophobicity of these nanocone structures. You can see the contact angle showing above 90 degree, which is a hydrophobic nature of these nanocone structures, and uh, this has the problem of integration these nanocone structures. So here is the schematic for the process flow of integration of two-dimensional materials to nanocone structures is showing. We have suppose a bare SiO2 on top of which have WSE2 on top of this, and then we coated the PMMA thin layer and kept it inside the water. Then after some time, the water get evaporate, water get peeled inside this, like you can see like this, and we have the WSE2 on PMMA layer, and then we can keep it on nanocone structures, and then we simply etch it out by using acetone. You can see the SEM image of these monolayers on top of the nanostructure. So these monolayers, these are really monolayers which have 0.8 nanometer thickness. So after that, we need to characterize the setup, these samples. So for that, we have setup. So in this setup, basically we have laser, so which have this dichroic mirror, which is 550, which allowing basically which allowing your the wavelength below 550 and transmitting wavelength above 550. Also, we have a halogen lamp source, which is basically at particular point we have to take photoluminescence spectra or any kind of spectra. So that is basically showing by halogen lamp, and then we have uh, two more lasers, which is supercontinuum laser from 400 to 800 nanometer, and then 635 nanometer lasers. So after that, these are for exciting wavelengths, and if we want to collect the wavelength, we have the spectrometer, which have silicon CCD, which is basically a visible range CCD, and then also we can do the quantum measurements by simply adding a flip mirror by using two APDs by Henry Brown twist experiment, and we can also do the polarization dependent measurement here by using just quarter wave plates and linear polarizers and rotating them. This is how the system looks like in the lab. Okay, so this is the optical characterization setup which we are using in our lab for all the measurements which I'm going to show. So here the photoluminescence of these WCTU integrated nanocones can be shown. You can see these nanocones are basically gold coated nanocones and PTFE coated nanocones, and you can see there is a clear enhancement is seen in the gold coated nanocones, which is approximately 8 times. So after the power dependence of these structures, you can see clearly 8 to 10 times enhancement is seen. So how this enhancement is coming? We need to know the origin of this enhancement, why this enhancement is coming. So for that, we did the simulations. So in simulations, basically we mimic these cavities in the simulation and see how much PL enhancement is coming in this basically by these cavities. For that, you can calculate the excitation enhancement and emission enhancements. Excitation enhancement is simple, the field enhancement due to the basically these kind of nanocone structures. So here you can see the gold coated nanocones are showing enhancement at near 532 nanometer excitation wavelength, which is our excitation wavelength. And PTFE versus AU gold nanocones, you can see 4 to 45 times enhancement is in the AU coated nanocones. So that means excitation enhancement is happening. After that, at these 3 points, we calculated the emission enhancement, and then you can see for different values of the quantum yield, we are getting approximately 6 times enhancement, while our experiments we are getting 8 to 10 times enhancement. So from where this extra enhancement is coming? So that extra enhancement is coming from the excitonic basically characteristics of these two-dimensional materials. So what happens? We basically we divided it into two components. One is the exciton and one is the trion, which trion is basically negative charged exciton or positive charged excitons. When positive or negative charge combined with the exciton, that is called basically your trion. So in our regime, there is you can see we have a linear. We are in the linear regime, so there is no issue in the device level. But if you will see the spectral weight, so exciton's spectral weight in the gold coated nanocone is higher. This red triangles you can see is higher than the exciton's correct exciton's spectral weight in uh, uh, PTFE nanocones. So which means the excitonic percentage is high in gold coated nanocones, and that is contributing in our basically in our you can say photoluminescence enhancement. Okay, we plotted peak position and FWHM also, so we can you can see we are getting little bit shift with respect to the power. That is showing you there is some strain is possible due to these nanocones structures. Okay, so we shown here about the photoluminescence enhancement. Further, from here we found that there is some strain is possible in these nanocone structures. So we started the study of the nano strain in these two-dimensional materials. So our question was, can we tune the emission of these excitons by using nanophotonic tools? Okay, so we did first the AFM, but since these nanocones are very high, so when we are going to do AFM, there is lots of roughness is there in these nanocones. So we are not able to do that with these kind of nanocones. So for that, what we did, we fabricated nanocones using e-beam lithography method. So that is a method to and grow the basically nanostructures. Okay, fabricate the nanostructures. So here is the schematic of the nanocone fabrication of nanocone structure is showing. You can see we took substrate as a size I2. Then we have 2% and 3% bilayer PMMA resist, which is a positive photoresist, and then we deposited it. Then we just irradiated the e-beam radiation, and after development of this we have this kind of structures, and on that we deposited the gold from e-beam evaporator method, and then we lift off this side PMMA, so that you can see we are getting such kind of gold nanocones. Here is the gold nanocone with PMMA with your WSE2 monolayer. You can see clear wrinkles are forming here, which is providing strain to these two-dimensional materials. Okay, so what happens when these two-dimensional materials feels the strain? What happens? This exciton drifts to the basically in the region where strain is high and band gap reduces, and this exciton recombines and gives us the basically localized strain. So we did the measurement of emission analysis. You can see this is on cone and this is on simple SiO2. You can see clearly you can see here like these wrinkles are forming in the SEM image. The same kind of emission is also seen in this for peak position as well as for the intensity profile in emission analysis, which confirms the these monolayers have strain. We further confirmed this strain by using Raman spectroscopy, and then in Raman spectroscopy we also find the same, that there is a shift of 1.5 centimeter inverse is seen due to the lattice change in the lattice vibration, and here you can see the standard deviation in the basically on cone and off cone is 6.91 and 6 point simple 0.57, which also showing we are getting like lots of you can say change in the Raman shift in on cone basically WSU2. Okay, so which confirms also our system is in strain and band gap is changing. Further, we did the KPFM analysis. So what is the KPFM analysis? First, I will explain that. So KPFM analysis is simple. Suppose we have a sample, we have a tip, which have some work function phi s and phi t is the work function of tip. When it comes in the contact, what happened? There is some difference will happen because of the alignment of the Fermi level. So Fermi level starts aligning for the sample and the tip. So there is a change in the basically uh, valence band happens, that valence band change, suppose is the VCPD, which is a contact potential difference. So what happened? We can apply this another VDC voltage to again keep it like this, so that we can get a basically exact value of CPD. So that CPD value is giving us the value for you can say uh, the change in the potential difference happening between the tip and the uh, sample. Okay, so here you can see we plotted the AFM image which is showing the nanocrystalline structures, and since these are very thin, have monolayer, so that is not visible here clearly, but in the phase image you can see the white region is clearly showing your gold nanocone structures. Okay, and here you can see this is a KPFM image which is showing the voltage profile difference, and in this point, this line is showing clearly, um, this line is clearly showing you this cone structures have basically changing the CPD values, which means we are getting a change in the work function due to the strain in these two dimensional materials. Okay, so now these two dimensional materials, as I said, have localization of due to strain. They can show localization of strain also. Just give me a minute. I need to have a call. This is an urgent call, actually. Sorry. Sorry for interruption. Okay, so this happens. After that, what we did, we simply. So my screen is visible, guys, na? Hello.
Yes, sir. Yes,
Huh.
sir. Yes, sir. It
So
is.
after that, we need to see these localized excitons or localized defect states can be visible in this or not. So for that, we took the HBN, which is a hexagonal boron nitride material, one of the two-dimensional materials. Why we are not using TMDCs? Because in the TMDCs, these single photons are possible at basically low temperatures because of the exciton phonon interaction in these two-dimensional materials. So that's why we took hexagonal boron nitride, one of the two-dimensional materials, and we studies the effect of plasmonic gold nanocones on quantum emission. Basically, quantum emission is called, you can say, single photon emission. So what we did, we did some literature survey, and in that literature survey we found that with the SiO2 or dielectric antennas have lots of applications on these single photon emitters, but plasmonic antennas have only one single paper, and that is also showing a G2 value of above zero point 0.5, which is not a single photon emitter in the range of single photon. So there is some problem happening in the with the plasmonics get integrated with the HPN. So for that, we first understand what kind of photon source exist in this nature. So for that, you can say there is a laser. Okay, you know about laser. So laser emit like photons, which are basically continuous photons of a single wavelength with the equidistance. Okay, basically they have uh, equidistance photons. Okay, after that, we have thermal photons. Thermal photons, like we are using light bulbs and anything in our rooms or anything, that is called thermal photons. That can emit the photons like this. So the random wavelengths will be there. Which photon will emit it at which time, we don't know that. Okay. Third one is a single photon source. So that means the rail of these photons is like this. So here you can see the single photons are coming at a equidistance or at specific times. So how we measure these photons? Okay, so to measure these photons, we measure this value, which is called a second order correlation G2 tau. In this setup, basically, which I shown. So here I have two APDs. Okay, one is this, one is this. Suppose we have laser. So IT and IT plus tau is basically intensities at these two APDs, which is avalanche photodiode. Okay, So these two will be equal because intensity of all photons in laser will be equal, right? So that can become IT square divided by IT square, and G20 will be 1. Okay. In second case, this value, this upper numerator value is greater than denominator value because of the randomness of these photons coming in this. One extra term will come, and G20 value will be greater than 1. For single photons, if this photon will become here, for single photon case, beam splitter will send the photon either in this direction or in this direction. So the one of the APD will show the value of I is 0. So that means exact value of G20 will be 0, but in experimentally there are lots of other photons are coming, so it is less than 1, you can say, okay, or less than 0.5. So hopefully you understand the photon source. So what we did, we again fabricated these nanocone structures and integrated this HBN monolayer with this by this setup. So this setup is also made by me in the lab, and this work is available in the online. You can search it. So basically, here these nanocone structures forms, and we can see this. Clear images of it. Further, we started the photoluminescence study. So in this photoluminescence study, you can see when HPN is on SiO2, there is no emission is there. Okay. While when this is on nanocones, you can see corresponding 2D map. You can see there is a clear emission is shown in the HBN when it is integrated with the nanocone structure. To further confirm, we used higher power of 1.2 milliwatt, and you can see this is showing in inset a clear image of this two-dimensional materials, and clear photoluminescence of HBN is showing with different phonon side bands and zero phonon lines. While this is a G2 measurements is not showing a bunching, because you can see at any point there is no G2 is less than 1. Okay. So further we try to find why this G2 is not coming to. So these are automatic experiments. Then we used manual measurements, and in the manual measurement we found a point where the narrower PL is seen, and that narrower PL is showing you uh, lifetime which matched with the HPN photons lifetime, and G20 is value also coming 0.44, which confirms that we have a single photon emitter in these HPN systems with plasmonic nanocavity. Okay, so that is one perspective of the single photon emitters, which is applicable for lots of applications like quantum computing, quantum communication, quantum sensing, and other kind of applications. Okay. So next and last, I think I have shortened the time, but I will take I think 2 or 3 more minutes. So can we engineer? So here what we did, some people reported recently there is a silicon nitride is a material in which there are lots of single photons are available. So we also tried to see that, but we did one part away from that. So we fabricated this ring resonators by using simple E-beam lithography methods, and we created a notch. So when we created a notch, you can see what happens when we have a incident light on basically curved surface or curved shapes resonators. What happens due to the total internal reflections, all the modes resonates inside this cavity. And if we can see 2D basically simple point scan, the these modes are looks like this. Okay, so that is called WGM, whispering gallery modes. This is basically a famous uh, dome in I think UK or somewhere. So that is basically acoustic due to you can say it comes from the acoustic theory we are assuming it. Okay, so what happens, you can see when we are on notch, you can see there are lots of WGMs on reality scene, while off notch there is no WGMs are. Okay, so that means we also did the saturation curve with red, which is showing we are We have saturation limit of very high at very high laser powers, which shows the we can make a device uh, which can helpful for high laser incidence also. You can see for notch, the the all modes are confined near to the notch. Okay, so that means these notches are helpful to confine uh, these two dimensional materials. So further we did the Q factor and basically analysis. So we are getting a quite good Q factor, which is good for lasing. So further we will basically, in summary, we fabricated the nanophotonic cavities by using colloidal lithography, beam lithography, and focused lithography. We developed the spectroscopic techniques for different kind of spectroscopic measurements. Then we have two-dimensional material processing and emission engineering in van der Waals materials, as well as PIC compatible silicon nitride materials. So there are my some of journal publications which I worked, and then thanks to my group and funding agencies for providing such kind of fundings, and I'm open for Q&A session.